black holes are one of the most important phenomena out there. And the reason is that for many years we cannot see the black hole and we don't know what it looks like. But in theory, we know what it looks like. It looks like black and it looks like a hole, meaning there's nothing there, right? But to study that, today is 3 key gravity experiments. The black hole is playing a role in all 3 of these experiments. And you might say, why is that? And that's because on a black hole is where the gravity is strongest. Not the ordinary gravity that we feel today, but the gravity is so strong that nothing can escape. Beyond this boundary, even light cannot escape. So this is a very strange concept, right? You fall in, nothing comes out. So in Taiwan, we actually play a very important role in this experiment. All 3 experiments, we used lasers as a standard method, interferometry, which is to combine light rays together in order to see the interference pattern. All 3 experiments use this kind of techniques, okay? And then in this particular one where Taiwan is working on, it's about making a picture of the shadow around the black hole. That image of the shadow tests general relativity, which is the last theory that Albert Einstein worked on. So there are very difficult concepts in there that we are trying to test over time. And I want to emphasize this is possible because the government support us. Government meaning you. It's your tax dollars, right? We're using your money to do these experiments. Of course, Jung Yuan is a strong research organization. We work with the universities, as Ming, and also with, very importantly, with the industry. So in Taiwan, our industry is very strong. They make many things. In this case, they also help us to do very, very careful experiments. So what does the picture say? It's black. Looks like a hole in the middle, right? So it's a black hole. So it has a very small size, as Wenping says, 42 micro arc seconds, right? Micro is 1/millionth of 1 part in 1/millionth of 1 arc second, right? The size scale is about if we put a donut on the moon and you want to be able to see it, that's how much resolution, how much power of the telescope you need in order to see a donut on the moon, right? So here's a picture of what it looks like in the center of our galaxy. Here's looking in from the edge of the Milky Way, looking in. We're on the outside, we're going in, and this is a picture in radio. You see many filaments. These are all due to supernova events. In the very middle, there's a supernova, and then there's a 1 dot in the middle, which we have seen for a long time. And now we magnify, 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 and it looks like a donut, okay? So this is the picture. If you are looking in the optical, it's just very dusty. In the radio, we can see all the way through, and you see the splash. All these splashes are actually supernova remnants, which is a star that has exploded. And then there seems to be some gas that's falling in towards the middle. These we have studied for a long time, the gas, but it turns out that the gas in the middle, there's some compact object. And this particular experiment is about the stars going around the black hole. This won the Nobel Prize 2 years ago. And now I tell you about the next experiment, which is why Taiwan is very importantly involved, okay? So in this experiment, Taiwan has put a telescope in Greenland. We also have 2 telescopes in Hawaii. We also have a big telescope that we joined in Chile called ALMA, which is the largest telescope in the world on the ground. It consists of 65 telescopes working together as an interferometer. So we combine all of these telescopes together to make a telescope the size of the Earth. Okay? on the ground, that's as big as we can get. So the figure of merit of a telescope is how big the mirror is and what wavelength you're working at. Okay? So the accuracy is how many wavelengths you can stick into a mirror. So if you use very short wavelengths, very big telescope, you can make a very, very accurate picture. So we push this in the radio because actually you can make each piece of telescope very accurately connected to all the other telescopes. Okay? Imagine you had a mirror, you broke it, and I only give you 8 little pieces of that mirror. And now I ask you to make the picture again. Not easy, right? How do you make 8 little pieces of mirror into one big mirror again? And the reason is that we're very, very accurate. We know exactly where the telescopes are. We know when the light is arriving at the telescope. We use atomic clocks to time the light coming in. And then we collect all the light again, and then we correlate them, make the interference pattern, and correct for it. This particular technology or technique itself won a Nobel Prize. Okay?